So this is chapter 8. We're discussing linear momentum and collisions. So momentum is a new physical quantity for us, and it's defined this way. Usually we use the letter p for a lowercase p, and momentum is mass times velocity. And it's probably it probably obeys your intuition of what your sense of what momentum is. A large object that's moving kind of fast generally has a larger momentum than a small object that's moving a little faster. So if we're looking in one dimension, we can drop the vectors. So in 1D, in 1D, we can just write P equals mv, and then we can say what is the momentum of a 100 kilogram football player traveling 5 meters per second. We just P equals mv, and that's 100 kilograms times 5 meters per second, which is 500 kilogram meters per second. Notice it's not a Newton, because a Newton is a kilogram meter per second squared, but for the units, it's mass times velocity. So in SI, it's kilogram times meters per second. Sometimes that's written as Newton seconds, right? Because a Newton is a kilogram meter per second squared, and if you multiply it by a second, you get kilogram meter per second. And so you'll see it both of these ways. So if you remember Newton's laws, we said that force was equal to mass times acceleration, right? That is Newton's second law. And acceleration is the change in velocity over the change in time. And so you can write, if you want, you can write the force is equal to the mass times the change in velocity over the change in time. And we can write the change in velocity as v final minus v initial over the change in time, right? But that's mv minus mv naught over the change in time. And so the force can just be written as the change in momentum over the change in time, because that's the final momentum, mass times v final, and that's the initial momentum, mass times v initial. And so the force can just be written as the change in momentum over the change in time. And this is really the way Newton wrote it when he wrote his original second law. We've kind of rewritten it this way for our beginning physics classes, but really this is the way Newton wrote it. So let me do an example. So Serena Williams' fastest serve is 58 meters per second. What is the average force exerted on a .057 kilogram tennis ball, assuming the ball starts from rest, and the collision time is 0.05 seconds. So here's her racket, right? This is her racket, and it contacts the ball, and then it hits the ball forward, right? And now the ball leaves. And so in here, all throughout here, there's a force. And actually the force varies with time. It starts out when it's just barely touching the ball, the force is weaker, and it gets stronger and stronger, and as the ball starts to leave, it gets weaker and weaker. And so if you wanted to look at the force versus time during those 5 milliseconds, the force would probably look like this, something like this. But we're just going to use an average force. And so this is the average force. Again, this time here is the collision time, and then and we're just going to assume it's a constant force, and it acts. It has this value through the collision time, and it's 0, of course, afterwards, right? So we can say, well, look, the force is equal to the change in momentum over the change in time, and that's equal to mass times the velocity minus mass times the initial velocity over the change in time, and that's equal to 0.057 kilograms times 58 meters per second minus, and this one's just going to be 0.057 kilograms times 0 meters per second. I don't even know if that's on there. Now it is. All right, times 0 meters per second, because the initial velocity is 0, all divided by 5 times 10 to the minus 3 seconds. And so the average force I get is about 660 newtons. And so that's maybe 120 pounds, something like that. More than that, 150 pounds maybe, somewhere in that range. So it's big force, right? It's just the change in momentum over the change in time. So in this problem, a ball has a mass of 2 kilograms, it's traveling at 5 meters per second. So mass is equal to 2 kilograms, velocity is equal to 5 meters per second. It's traveling 30 degrees above the x-axis, so this is the x direction, right? So we can say that's the y direction. What are its x and y components of momentum? Again, since momentum is mass times velocity, right? This is going to be a vector. It's just going to have the same direction as the velocity. It'll just have a different magnitude because it's multiplied by the mass, right? And so if I wanted to figure this out, I would say, well, look, this guy's the magnitude of momentum of this guy is just the mass times the magnitude of the velocity, which is 2 kilograms times 5 meters per second, or 10 kilogram meters per second, right? And so that's the momentum in this direction, right? And so I can say P equals mv equals 10 kilogram meters per second. And so that's what that vector is. Say, I can just leave that guy off now that I've got him included there, and I can say, look, this is my piece of y, and this is my piece of x, right? And so I can say piece of x is equal to p times cosine 30 degrees, which is 10 kilogram meters per second, times 0.866, which is 8.66 kilogram meters per second, or 8.66 Newton seconds, depending on which unit I want to use. Similarly, piece of y is p sine 30 degrees, which is 10 kilogram meters per second, times the sine of 30 degrees, which is 0.5, which is 5 Newton seconds, or 5 kilogram meters per second. So we're going to talk about impulse. If we start with Newton's second law in momentum form, we can multiply both sides by delta t, and we say, look, the change in momentum is the force times the change in time. This comes up in lots of sports. So for example, the change in momentum of a football is the force that's exerted for the football on the football times the amount of time that force is exerted. So if you're kicking a football, how long is your foot in contact with the football and how strong is the force? That determines the change in momentum. If you're hitting a baseball, the same thing. What's the force on the baseball by the bat, and how long is the bat in contact with the ball? Shooting a basketball, same thing. The change in momentum of the basketball, remember, this is just the mass times the change in velocity, is equal to the force times the change in time. So you might have heard coaches are always saying what? What does your coach say when you're hitting a baseball or shooting a basketball? 2 words. See if you can think what it is. You can pause it. Follow through. Right? Follow through. What they're saying is make delta t as long as possible. Have your bat in contact with the ball, or your club in contact with the ball, or your tennis racket in contact with the ball, or your hand in contact with the ball for as long as possible, because that gives you the greatest change in momentum. You want to push on that ball for as long as you can. If you can double the impulse time, if you can double the impulse time, you can double the change in momentum. And so we can do a quick example here. We can say, look, Bob hits a golf ball with a force of 8,000 newtons. That's a typical club force on the ball during the collision. The club is in contact with the ball for 0.0005 seconds. That's a typical number. So it's like half of 1,000th of a second, right? It's 5/10,000ths of a second. What's the impulse? And so the impulse is just a force times the change in time, which is 8,000 newtons times 0.0005 seconds, or 8 times 10 to the third newtons times 5 times 10 to the minus 4 seconds. I can do that a little easier. So that's 40 times 10 to the minus 1, or 4 newton seconds, right? So that's the impulse. And that's equal to the change in momentum. And so the change in momentum is 4 newton seconds. Now I can ask the question, if the mass of the golf ball is 0.046 kilograms, which it is approximately, right? What is the velocity of the ball after the collision assuming it started from rest? Right, so I know that the impulse is 4 newton seconds, and I know that the mass, I'm going to erase this part, right? And I know that the mass of the golf ball, so I can say, look, delta P is equal to 4 newton seconds, right? That's what we figured out down here. The impulse is 4 newton seconds. But that's just mass times V final minus mass times V initial is 4 newton seconds. And that, since this guy is 0 because it started from rest, then I get the velocity, the final velocity, is equal to 4 newton seconds divided by 0.046 kilograms. Right, so I have to do that on my calculator. I get about 87 meters per second, something like that. That's the final velocity. So that's impulse.